Hello, I'm Mo. I'm from Nokia and I'm a researcher at Bell Labs. We've been doing a lot of work on 6G sensing. And today I'll be talking about self-supervised learning and how we made it work for 6G sensing. This is joint work with my colleagues Akash Singh and Max Arnold. Okay, so this is the summary of the talk. I'll start with a bit of motivation and use cases, and then we'll move on into the details of our approach and experiments and wrap up with a summary of findings. So why do we want to do sensing in radio? Well, if we can do sensing in radio robustly, this will enable a multitude of applications, including, say, lamppost sensing in the urban setting. However, it has been traditionally difficult to implement radio sensing because radio signals are not straightforward to understand and interpret by people. When people think about radar or sonar sensing generally, they might think about, say, submarines tracking other submarines underwater, which historically required a pair of human eyeballs, as shown here. This had involved the human operators developing a nose or expert knowledge, if you will, for those object signatures that we want to track. A bit later, we tried to codify this expert knowledge in software. So in a nutshell, we want to automate all that. However, there are non-trivial technical challenges if we actually want to automate the process of accurate object sensing with radio. And the core part of the challenge is knowing what a thing looks like in radio. Machine learning can help us figure this out. However, the model still needs to be trained on known data, which circles back to needing people in the first place to label the data. So the question is, how might we obtain the ground truth labels to automate radio sensing with machine learning? There are two reasons why automating this workflow is tricky. One, radio heat maps are hard to interpret. As shown in the figure on the right, we get complex target returns, which we then need to label one by one, consulting a paired image. Two, this laborious labeling process has to be repeated at scale because machine learning requires quite a lot of data to train on. And if you're a certain automotive company, you can have 1,000 people department within your organization whose job is to only label data. Clearly, this is not ideal and does not terribly fulfill the promise of machine learning for making people more productive. We at Nokia have had a bit of experience ourselves in the indoor radio sensing space. Specifically, our team in Sunnyvale have spent quite a bit of time building and automating flows for supervised machine learning for radio sensing. Let's shift gears a bit and look at what has been happening in computer vision recently. Self-supervised learning is the paradigm of next generation learning systems. In SSL, models are learned by making them predict – 'fine-grained properties about the data. This is in opposition to thin labels we usually attach to data in the case of supervised learning. Because of this, SSL has much higher information conversion ratio during training compared to supervised learning. There has been a growing body of literature reporting on successes in self-supervised learning for vision. Google in Sinclair first showed new compelling results for computer vision using self-supervised learning, whereby no labels are required for machine learning. This work was then followed by many more refinements and optimization of the idea of the SSL for vision, notably with Facebook's momentum contrast, and recently in audiovisual SSL video learning by Microsoft. And culminating with a billion-scale demonstration of vision SSL at Meta for more robust and fairer computer vision models. So leveraging this new learning paradigm, we at Nokia have formulated our own radio-visual SSL problem. The idea is to tap into the mutual information between paired camera images and radar heat maps to automatically learn a radio sensing network. This learning formulation happens in a totally label-free fashion. Effectively, vision teaches radio how to make sense of the environment via MI, mutual information. Once the radio network is learned, we can then specialize it for any downstream sensing task we are interested in. We have demonstrated radio-visual SSL on an empirical data set. It allowed us to build a 4-category classification task for now on the radio part of the SSL network. For the technical details, please consult the paper. We use the COO dataset from the University of Washington. It has about 30 to 40K paired camera heat map data points. It uses FMCW radar in the 77 gigahertz automotive band. It supplies us with 4 scene labels: pedestrian, cyclist, car, and empty. These labels map naturally to many of the envisioned use cases for 6G, for instance, safety applications. In terms of main outcome of this investigation, we found that a sensing model trained by SSL on our dataset always outperforms a fully supervised baseline, regardless really of how many labels are available. This is in line with findings from Vision SSL, and it can be understood by noting that SSL has fundamentally higher information conversion ratio during training compared to supervised learning. The quality of the SSL pre-trained representation is corroborated by looking at how many training epochs it takes to fine-tune for a specific downstream task. Indeed, in our experiments, around 30 epochs suffice to build the downstream task. Right, so to conclude, we show that vision can teach radio to sense without labels on empirical real-world data. We demonstrate that this is not only possible, but is also better than learning a radio sensing network in a supervised fashion. We expect more gains in the future as we scale our evaluation, again, noting what I mentioned earlier about the fundamental higher information conversion ratio of SSL during training. The key takeaways of this work are: A, SSL for radio sensing is infinitely scalable. So we can do without an army of labelers for machine learning to work. And B, learning a sensing representation via SSL is a good way to hedge your bets on what sensing applications might you want to build in the future. Right, I think that's it for me for now. Thank you very much for your time and attention, and please check out our paper and the proceedings for future details. Thanks a lot. Cheers.